Hello everyone, and welcome back. Today we're going to be continuing our exploration of multivariate statistical analysis and describe a couple ways on how you can assess the multivariate normality of your sample in the case where you don't actually know if your sample does come from a multivariate normal distribution. So keep in mind that if you do come from a multivariate normal distribution where you have two or more variables, let's say xi and xj are two of them, if you look at the cross-section between those two variables, the cross-section you're going to get is actually going to be an ellipse. So if you look at this ellipse, there's going to be two vectors that are orthogonal to one another. So those are going to be the eigenvectors associated to variables xi and xj, and you'll be able to figure out which one is which depending on the eigenvalues and their associated correlation with their associated individual variances. And the direction, obviously, of this ellipse is associated to the correlation between I and j. So in this particular picture, if it's drawn to scale, we have a positive correlation between I and j. Right, but what's most important about this cross-section is that it is elliptical. So we have an elliptical cross-section with our multivariate normal distribution, fx. Now, of course, we can scale this ellipse out. So for example, we could have that one. It's still going to have the same exact eigenvector, just scaled by some chi value, because if our x1 and x2 do belong to the same ellipse, then they have the same what? The same z-score. But z-score usually isn't a phrase that's commonly used in the multivariate world, so what we usually do is replace z-score with the word Mahalanobis distance. Mahalanobis distance, right? So as long as you're on the same ellipse, you have the same exact Mahalanobis distance from the mean, right? The same z-score from the mean vector of that particular object. Now, if that is the case, then what do we have? So recall the Mahalanobis distance, so the Mahalanobis distance between a random vector x and the mean random vector x bar, this is going to be equal to the square root of x minus x bar transpose times the inverse of the associated covariance matrix of that multivariate normal distribution or multivariate distribution minus x bar. And remember that if it is multivariate normal, then these are going to be associated to a chi distribution with d degrees of freedom. Or if you don't have a chi distribution calculated for chi critical values, you can do a chi squared d distribution if they are the squared distances. So squared Mahalanobis distances follow chi squared, and just Mahalanobis distances follow a chi distribution. So if they follow a chi distribution, then the Mahalanobis distances for a multivariate normal sample should also follow a chi or chi squared distribution. So for example, so as a guiding example, for d is equal to 2, if somebody asks you, let's assume you pick a variable or a vector x from a multivariate normal distribution, and I ask you, what is the probability that the Mahalanobis distance of that random vector x with respect to its mean vector mu is less than or equal to 1, and keep in mind 1 squared is also equal to 1, one can find that, again, if it's multivariate normal, then that should follow a chi-square distribution. So you can find that that's approximately equal to 3935. And if somebody asks you what's the probability that the squared Mahalanobis distance between x and mu is less than or equal to 2 squared, aka 4, then one can find that's approximately equal to 0.8647. And similarly speaking, what's the probability that a randomly selected multivariate random vector from a multivariate normal distribution between that point x and that vector mu is less than or equal to 3 squared, aka 9, one can find that's going to be approximately equal to 0.9889. And in case you don't know where these are coming from, you can do a p chi-squared in R, for example. And what are we really comparing these to? So these are analogous to our d equals 1 values of 68, 95, 99.7, which a lot of you probably memorized a long time ago when you were studying just basic elementary statistics. Right? So 40% of our values should have a squared Mahalanobis distance of 1 or less. So if you have a bunch of your points in your sample that have a Mahalanobis distance less than or equal to 1 between their mean vector x bar, because keep in mind we don't know what mu is, so we have to approximate that with an unbiased vector estimator, x bar. So if you do x compared to x bar and calculate all of your Mahalanobis distances, then if you find that 90% of your values have a Mahalanobis distance that is less than or equal to 1, you probably don't have a distribution that is associated to a multivariate normal of dimension 2, right? Keep in mind, obviously, depending on dimensions, these numbers are very, very different, so keep that in mind. So what we need to do is we need to analyze the Mahalanobis distances and see if they follow a chi-squared distribution. So a qualitative method that you can do is going to be parallel to like an NQQ plot for univariate analysis, and I'm going to call these plots MQQ plots. So MQ is going to be associated to Mahalanobis distance quantile, and Q is going to be representing the quantiles from our sample. Right? So what is the first step that we need to do in order to generate a Mahalanobis quantile plot? So the first thing that we would obviously have to do is calculate the squared Mahalanobis distances of x with respect to x bar, and that's going to be done for all vectors x in our multivariate sample S, right? And keep in mind these vectors x and xd belong to d-dimensional space, okay? So these are going to be our empirical quantiles, and make sure that you sort them from least to greatest, right? And let's assume that I define these Mahalanobis quantiles in a vector. Let's call it MC, just for semantic purposes. So the second thing that I need to calculate is calculate my theoretical quantiles. So calculate my theoretical quantiles, which I'm going to store in a vector. Let's call it MT. So my theoretical Mahalanobis distances. So how am I going to do that? Well, my Mahalanobis distances should be following a chi-squared d distribution. So this is going to be a chi-squared d distribution. And what we need to do is we need to stagger our points or endpoints along this domain. So we're going to have these points here. So once we get to here, they're going to be sort of clustered together, and then they're going to sort of scatter out there. So it's going to be x1, x2, x3, all the way down to your last point, xn. So if we project these points upward, it's going to partition our area, which sums up to 1, into m plus 1 regions, where each of them, that area, that area, that area, is equal to 1 over n plus 1, right? So these are, that's the 1 over n plus 1th quantile. Then it's going to be the 2 over n plus 1th quantile, and so on. So it's pretty much the same exact thing that we did for normal Quantile-Quantile plots, but instead of sampling from a standard normal, now we're going to be sampling from a chi-square distribution. So in the R realm, what you could do is, for example, MT is going to be equal to Q chi squared, and then we can create a sequence from 1 to n, increment by 1, and then divide each of them by m plus 1, sample from a D distribution, and since we're going from least to greatest, we're going to do lower tail is equal to true there. So that's going to be our theoretical Mahalanobis quantile plots. Keep in mind Mahalanobis distances squared are always positive, so we don't need to worry about the negative side of our graph. So the third step is to plot our m values. So m, what did I call them? Empirical versus m theoretical. All right, so our empirical versus theoretical quantiles, right? So once we graph them out, keep in mind if they are extremely correlated, they should line up one-on-one with each other. So this is still going to be our basis values. You could put your empirical quantiles on the horizontal, your theoreticals on the vertical, or vice versa. It doesn't really matter. And then you're going to be plotting those points, and hopefully they lie on that line. But if you get a bunch of points that are sort of all above or all below, then that's definitely a really big issue, because the correlation between these should be closer and closer to 1. So if we do the correlation between, for example, ME and MT, that should be close to 1 or -1. So you could do the absolute value, or you could do r squared. It doesn't really matter, but those points should lie on that line. But the downside with Quantile-Quantile plots in general, whether it be normal Quantile-Quantile or Mahalanobis Quantile-Quantile, is that these graphs are typically very subjective, because they are qualitative methods, not numerical or quantitative methods. So are there any quantitative methods out there for testing multivariate normality? Indeed there is. There's actually several out there, but let me introduce one of them that is actually very, very used in practice and very, very robust. So one quantitative test that you can use to assess the multivariate normality of your sample, or if you have many samples, if you're doing like a MANOVA test, is called the Hanze-Zirkler test for multivariate normality. So what this is going to do is this is going to follow sort of parallel to your Kolmogorov-Smirnov test, your Anderson-Darling test statistics, your Lilly for test statistics, and the rest of them, right? So it's going to sort of follow that realm, but it's actually not going to compare their cumulative density distributions, because cumulative densities do have a slight nuance to them when you're working in higher dimensions compared to a one or univariate sample. So the Hanze-Zirkler test is still going to take advantage of the Mahalanobis distances and the chi-squared nature of them if they were truly associated to a multivariate normal. So the very first thing that you need to do when it comes to calculating a Hanze-Zirkler test statistic is to again calculate your empirical. So calculate your empirical squared Mahalanobis distances. So that's the first thing that you have to do, just like we did with our Mahalanobis Quantile-Quantile pop. So what we're going to do is we're going to have our Mahalanobis quantiles, which I'm going to call, for example, Nj. So it's going to be equal to the squared Mahalanobis distance between xj and x bar. So that's going to be equal to, again, xj minus x bar transpose times our sample covariance matrix inverted times xj minus x bar. Right? So that's the first thing that we need to do. The second thing that Hanze-Zirkler does is it calculates the weighted Mahalanobis distances. So what's going on here? Well, first off, let's define what we mean by a weighted Mahalanobis distance. So the weighted Mahalanobis distance, which I'll define as little wj, is going to be equal to 1/2 e to the power of minus 1/2 times our squared Mahalanobis distance, mj. Okay, so one may ask, well, why can't I just use the squared Mahalanobis distances? Why do I have to, transform them into this new domain? So a couple points that might allow you to sort of see the motivation in this particular transformation is the following, which we actually investigated when we actually started looking at higher dimensional probability density function. So as the number of dimensions increases, what happens to the points of our distribution? What you actually see is the points actually move to the boundary of our density function. Right? And you can clearly look at this and look at the percentage of values that are within one Mahalanobis distance from the mean, and look at that metric as d goes to infinity. And what you're actually going to see is that the area or the volume or the hypervolume actually goes to 0, and the percentage of values whose Mahalanobis distance is like greater than 7 actually goes to 1 as d goes to infinity. So it's actually quite counterintuitive. So what you have here is, okay, the points are going to move towards the boundary of our density function, which means that the Mahalanobis distances are going to go in the majority are going to be in the tails of our chi-square distribution, because these dm squareds get bigger and bigger and bigger because we're moving towards infinity. So let's actually say the majority of these d squareds are in the tails of the chi-squared. Not all, but the majority of them. So if that's the case, so why would we actually look at these weighted values? So if the Mahalanobis distance of a particular point is approximately equal to 0, that means we're close to the mean, that means the weighted Mahalanobis distance is going to be equal to e to the 0, which is 1, so that's going to be approximately 1/2. So if the Mahalanobis distance is really, really large, which is very common for the multivariate case with higher dimensions, what you're going to actually see is that the weighted Mahalanobis distance is actually going to be equal to what? So as m goes to infinity, e to the minus infinity goes to 0, and 0 times 1/2 is 0. So that's approximately equal to 0. So we have everything from 0 to infinity accounted here on the majority scale from 0 to 1/2. Right, so at least from the analytical side, this is a nice range to analyze our Mahalanobis distances in. Right, so that's one of the motivations as to why this is the case, and there's some asymptotic moment-generating functions reasons also why this is very, very useful. So once you have your weighted Mahalanobis distances squared, the third step is to calculate your Hanze-Zirkler test statistic. So the Hz test statistic is defined to be equal to n, the total number of people within your multivariate sample, plus 2 times eta 1, and I'll describe what that eta is in just a moment, times the sum from j is equal to 1 to n of your weighted Mahalanobis distance, and then plus eta 2, another constant, times the sum from j is equal to 1 to m of our squared weighted Mahalanobis distance minus m. Right? So this is our Hz test statistics, and you might be wondering, what is this eta 1 and eta 2? These are constants that are asymptotically dependent only on the dimension you're working in. So for one dimension, you'll have eta 1, eta 2. For 2 dimensions, you're going to have eta 1, eta 2. For n dimensions, you're going to have eta 1 and also eta 2. Right? And depending on how close it is to multivariate normal, some etas are actually a little bit better than others. Okay? So those eta 1s, eta 2s, not very easy to calculate in the slightest, but they do depend practically only on D. So we have this Hz test statistics. So a nice little question is, what distribution does this Hz test statistic follow? Does it follow a chi-squared? Does it follow an f? Does it follow a z? Does it follow a t? No. So since it doesn't follow a special one, at least that I've mentioned, we can just say that it follows a Hz distribution. Right? So a Hanze-Zirkler test statistic will follow a Hanze-Zirkler distribution, especially if your sample sizes are relatively small or moderately large or what have you. Right? So a very useful tool in this particular case is Monte Carlo simulations, because you can do Monte Carlo simulations on this Hanze-Zirkler test statistic. And for example, you could even drop this eta 1 and eta 2, but you could view that eta 1 and eta 2, or D, moreover, would be a degrees of freedom for your simulated Hanze-Zirkler distribution, right? So keep in mind with that if you do decide to modify this Hanze-Zirkler test statistic. Now, in this particular form, even with the eta 1 and eta 2, even if you don't know them, there's actually a very beautiful theorem associated with it. And it says, as n goes to infinity, the Hanze-Zirkler test statistic will actually converge to a z test statistic, right? So that means you can compare this versus a z critical value, and in particular a two-tailed critical value, or you can even use a one-tailed critical value if you have evidence to believe that all of your Hz test statistics are substantially positive in the upper tail. Right? So that is very asymptotic though. Like if n is like bigger than 100, bigger than 1,000, the closer and closer the better. But keep in mind, if you use a z-crit for small values of n, then the Hanze-Zirkler test statistic will not at all resemble a standard normal distribution. So since it doesn't satisfy this asymptotic relation, you definitely need to be using software to calculate, for example, A to 1, A to 2, or more over this HZ test statistic. So for example, if you're working in the R realm, if we're using the library MVN, so the MVN library has the Hanze-Zirkler test statistic implemented. I believe it's HZ_TEST. Just feed your multivariate sample in there, and it's going to give you your test statistic and associated p-value. It'll do all the nasty math for you. In some sense, you could do this if you had like a Hanze-Zirkler table of critical values to compare this to, but you would again have to calculate your A to 1 and A to 2, which is again very numerically intensive, right? So either you can use this library in the R world, or you could do Monte Carlo simulations to simulate this HZ test statistic with A to 1 and A to 2, for example, be dependent on, say, M, or D, I mean, and D being your quote-unquote degrees of freedom, I guess you could say. Or you could build your own test statistic on multivariate normality, but you just have to be very, very clever that it is actually testing what you seek out to test, right? But these are two common methods, the multivariate Mahalanobis-Quantile plot, which is very subjective, but it's a good starting point to analyze things. And also the Hanze-Zirkler test statistic and Hanze-Zirkler distribution, which is definitely more on the software side of implementations, because on hand is definitely not that useful, but at least you should have some insight from this explanation, sort of what it's doing and why it's doing it. And if you look at these this test statistic structure of what we're going on here, you could actually see that, okay, maybe that's approximately a chi-square distribution. That's definitely probably a chi-square distribution. So maybe we're looking at, because keep in mind the squared Mahalanobis distances follow chi-squared. So we have, for example, e to the minus chi-squared random variable plus a chi-squared random variable. So what type of distribution is a chi-squared plus a negative exponential of a chi-squared random variable? I don't know, but at least from this structure, it's a HZ random variable, whatever that means. So anyway, I hope this gives you some insight on how you can actually go about testing multivariate normality, whether it be software or whether it be MQQ plots. So I hope you enjoyed this video, and I'll see you in the next one. Take care and be safe.